Today we would like to move on to group delay and dispersion. But before we do so, let's briefly review the concept of instantaneous frequency that we had introduced in last week. Just a brief review. Okay. As I mentioned, in general, nonlinear phase modulation will result in a new spectrum, but a useful point of view is by the Fourier transform property. We have known a frequency shift in the frequency domain is equivalent to a linear phase modulation in the time domain. So we can generalize the concept. So whenever our phase modulation is nonlinear, such as the cell phase modulation effect we have introduced, then the frequency shift is simply the time derivative, prime. Here, prime means time derivative of the nonlinear phase modulation. So the instantaneous frequency, omega instant, is equal to the carrier frequency, omega 0, plus the time-dependent frequency shift, which is first-order derivative of the phase modulation. Okay, and last time I showed you two examples. Here is a very brief review. For example, if we assume a time domain function f of t like this, the red one is the intensity profile. The blue dashed curve means the phase profile. Here we assume the temporal phase is initially a constant phase. And the gray one is the corresponding spectrum in the frequency domain. Then what happens if we apply a linear temporal phase modulation? Temporal phase is big omega constant times time variable t. So this is a linear function of time. And based on the formula in last page, we know after time derivative, big omega times t after derivative is a constant big omega. So it predicts a constant shift of angular frequency, big omega. So illustration is like this. You have a linear function of phase in the time domain. It will result in a constant shift in the frequency domain. So from the gray spectrum to the blue spectrum, the shape is preserved, but the position is shifted by an amount of big omega, which is the slope of the phase modulation in the time domain. So this is the easier case. The second example is quadratic temporal phase function. Okay, this time we still have the same power spectrum, but with a quadratic temporal phase function. Say it's equal to sigma over 2 times t squared. So this is a quadratic function, purely quadratic function. The question is, what is the corresponding spectrum in the frequency domain? Okay. Again, we apply the formula, just performing first-order time derivative for your phase modulation function. And it's well known, quadratic function after time derivative, it's a linear function. Okay, so we got sigma times t. The frequency shift is a linear function of time, sigma times t. So how about the illustration? Okay, say we observe a time instant t1 here. t1 is an earlier time. Okay, smaller than 0, so it means earlier time. And if you substitute t equals t1, you got a spectrum like the red curve, because this time your frequency shift sigma times t1 is a negative number. So the central frequency is actually smaller than the carrier frequency omega 0. So your center is shifted to the left compared with the original spectrum without any modulation. Okay? But if you observe a later time instant, say t equals t2, okay, t2 is here, it's a positive number. So based on the formula, we know this time the frequency shift is a positive number. So your spectral center is shifted to the right. Okay? So we got something like the blue spectrum. Okay? So if you observe earlier time here, you got a spectrum like the red one, the central frequency is lower. If you observe a later time like T2, the center frequency is higher. So you can imagine the fringe density underneath this temporal profile will change with time. The density is lower at T1 but higher at T2, right? If you observe the corresponding spectrum in the frequency domain. So that's the impact of nonlinear temporal phase modulation. Okay. Good, but there are more things we need to elucidate. Let's review the cell phase modulation effect we have introduced. Imagine we have a temporal intensity profile like this. I of t is the time domain intensity. Look like a Gaussian profile. Okay. Then what is the corresponding phase modulation curve in the presence of SPM? Okay. Do you still remember the relation between the phase modulation function and the input intensity function? Basically, it's in proportional with each other, but with a minus sign, right? So you can roughly draw the temporal phase modulation curve like the blue dashed one, okay? If your N2 coefficient is positive, which is always true, we know the phase modulation function is proportional to actually minus I of t. I of t with a minus sign. And your I of t is a pulse. There is always a central peak. So minus I of t always has a central value, right? So the blue curve has a central value like this. Next, what is the frequency shift or instantaneous frequency? As we just briefly review, your frequency shift function is proportional to time derivative of your phase modulation, right? So just try to manipulate the derivative for the blue curve. What do you get? We know for the left half, your slope is always negative, right? So your after derivative, you always has a negative function value. For the right half, your slope is always positive, so you got positive for the right half about the frequency shift. But you can also observe at the beginning here and the middle point, your slope should be 0, right? The blue curve's slope is 0. So you have 0 frequency shift at the beginning and at the middle, and for the same reason at the post tail, you will have 0 frequency shift. So roughly you can draw the frequency shift function like the green curve, okay? And you can say the post leading edge, which is roughly here, has a negative frequency shift, or it corresponds to red color. Okay, red means lower frequency. For your post trailing edge, your frequency shift delta omega is positive, that means the local frequency is higher. So you can roughly say your pulse tail is bluer. Okay, blue color means higher frequency. Okay, so leading edge, red. Trailing edge or pulse tail, blue. Okay. And if you draw the electric field, E of t, you have to draw the fringes, right? So the observation tells us the leading edge has a lower oscillation frequency, and the trailing edge has higher oscillation frequency. So you have your local frequency actually increases with time from lower frequency to higher frequency. It's not a constant. It increases with time. Okay? And the nature of local frequency or fringe density increases with time is coined as upchirp. Okay? Upchirp. But this is true only around the pulse center, which is highlighted here, okay? In this region, your instantaneous frequency is monotonically increasing. So it's a standard upchirp region. But for here and here, things are different, right? Here you have fringe density decreases with time. Here, same thing, okay? So for the very beginning and the very last moments, you have downchirp instead of upchirp. But for your pulse center, this is a monotonically increasing function. You have a standard upchirp, okay? But because the most of the pulse energy is contained around the pulse center, right? So roughly speaking, cell phase modulation creates upchirp for your pulse. Your fringe density increase with time, like this figure. Okay, but if you want to precisely draw the fringe curve, this is not true, right? You can imagine in the very beginning and the very last moments, the local frequencies differ from the simple upchirp model. It's a little bit complicated. But since the pulse energy there are very nominal, so we can roughly mention that cell phase modulation creates upchirp for your input pulse. Okay, any question? Please.
With the shape of the envelope changes.
You mean at the output, whether I of t will change or not?
I mean E of t.
E of t. Basically not. Here, cell phase modulation is a pure phase modulation mechanism. It will not change your intensity profile. Okay, so if you have a Gaussian input, here envelope is always Gaussian. It does not change. Okay? But I have to emphasize this is only true when you only consider single mechanism, SPM. In reality, there are multiple mechanisms simultaneously occurring. Then this simple model is no longer true. We will briefly discuss the interplay between multiple mechanisms at the end of this lesson. But here, we only focus on SPM first. Okay. Any other question? And another important behavior of SPM is it can create new frequency components, or simply speaking, broaden your spectrum. Okay? And this mechanism is very useful in a couple of applications. Okay? But the idea is quite simple. The left figure is almost the same as we just saw in the previous slide. Okay? You have a Gaussian input intensity I of t. You have a nonlinear phase modulation curve with a central valley. But here I designate the maxima difference of your phase function, or phase modulation function, as delta phi max. Okay? And you can imagine the higher your peak intensity, the larger your delta phi max, right? If your delta phi max is much smaller than pi, then cell phase modulation effect is unimportant. But if your peak intensity is higher and higher, eventually your delta phi max could be many pi's, then SPM effect is important. Okay? So here I designate the modulation depths of SPM as delta phi max. And as in the previous slide, the green curve represents the instantaneous frequency shift due to the nonlinear phase modulation. And I also designate the maxima frequency shift. Okay? Here is 0, means the local frequency is the same as the carrier frequency, no frequency shift. And here you got the maxima frequency shift. And the number is designated by delta omega max. Okay? And what is the relation between delta omega max and the delta phi max? They are not two independent variables. They are closely related with each other. What is the relation? You have to apply the same formula I just introduced. How do you get the green curve? From the blue curve. A time derivative, right? So could you estimate, just estimate, not precisely calculation, okay? How do you estimate delta omega max? You can imagine the green curve is the slope function of the blue curve, right? So where is your maxima slope in your blue curve? It's maybe somewhere here, right? You got the maximum slope. And what is the number? How do you estimate the maximum slope? You can apply the difference quotient as you studied in calculus, right? 差商，对不对？你怎么得到一阶微分？就差商取极限嘛，对不对？ What is your difference quotient? You have to estimate the shift along the horizontal axis and the shift along the vertical axis, right? The shift along the vertical axis is here, delta phi max. And what is the corresponding horizontal shift? Maybe just use the post duration, right? Your post duration, about half of the post duration within this time interval, your phase change is from 0 to delta phi max. Okay? So the slope is roughly here. Okay? 2 times delta phi max over delta t. Okay? So you can see by this formula, how do you create a very large delta omega max? Okay? You have two options, right? One, increase your delta phi max. And as I mentioned, delta phi max is proportional to your peak intensity. So you have to increase your peak intensity of the input pulse. You can have a large frequency shift. The second choice is reducing delta t. Okay? If you cannot increase the peak intensity, maybe you can compress the post duration. Either way, you can get a larger frequency shift. Okay? But the right figure is something new. The gray one is the original spectrum of the input pulse. And here I specify the bandwidth by delta big omega, the input bandwidth. Okay? Then, if this condition is satisfied, maxima frequency shift is larger than the input bandwidth, delta big omega, then this will happen, right? This is your carrier frequency, omega 0, right? And according to the green curve, we know the maximum frequency shift is delta omega max. If this is bigger than your bandwidth, it could be here, outside of your original spectrum. Correct? And for the same reason, you can create low frequency components as well. So you can have red components, new red components beyond the original spectrum if your delta omega max is big enough. Okay? Then with this picture, you can roughly say after the cell phase modulation, more frequency components will be created from the regions where there was no power at all in the beginning. But due to cell phase modulation, if the effect is strong enough, your spectrum can be broader. Okay? Is it okay for you? And clearly, this must be a nonlinear effect, because we know within the regime of linear optics, no new frequency components can be generated, right? You can perform amplitude modulation, phase modulation, but you cannot change your color. That's within the linear optics. Here, SPM is apparently a nonlinear effect. So if the effect is sufficiently strong, now you can distort your spectrum. You can create new frequency components. It's possible because SPM is nonlinear. Okay? But if delta omega max is too small, say it's smaller than your bandwidth, delta big omega, then SPM might create frequency components here, here and here, but they are already within the original spectral range. So you can hardly tell any spectral broadening. The spectrum looks similar as the input. Okay? Only when your delta omega max is big enough, you can see the difference. You can see the spectral broadening effect. And the rule of thumb is like this. If your input pulse is Gaussian pulse, okay, then the output spectrum can be broadened by delta phi max times, by a factor of delta phi max, provided that delta phi max is big enough, much larger than 1. Okay? So for example, if your delta phi max is 10 radians, which is very big, then the output spectrum could be broadened by 10 times. It's a very significant spectral broadening. But if your delta phi max is 0.1 radian, it's very nominal, then your this condition is not satisfied. So you cannot conclude the output spectrum is only a fraction of the input spectrum. It's not true. Okay? So this rule of thumb applies only when your SPM is sufficiently strong. Delta phi max is much greater than 1. Then this rule of thumb basically applies. But remember, it's up to your input pulse shape. Here we assume Gaussian pulse. If you have other input pulse shapes, the rule of thumb could be different. Any question? Please?
The real sentence, the estimation of
Yep.
delta omega max, is it only holds for Gaussian pulses?
Yeah, yes. If your shape is very different, this estimation is no longer true. Okay. But it's only for convenience. 不用太计较这个详细的这只是个估计而已，只是告诉你两者之间有关系，如此而已。定量上它可能这个是不是真的2呢？可能还有很多的差距在里面。只是借这个例子告诉你，这个是来自蓝色曲线的斜率，那斜率大概就是水平位移分之垂直位移去估来的。我只是这样，只是做这件事而已。